Beliakova from Zürich. And right after the talk, we have a wine reception in the lobby upstairs.
In the lobby.
In the lobby.
Thank you very much. So thank you to Jake for the invitation. It's a big pleasure to speak here. So I'll basically will report what is done on the mathematical side towards development of Richtich-Drive invariant into some power series and some formal parameter. And this is a story about so-called unified invariants, which were first constructed by Habiro for SL2 and then extended to all semi-simple Lie algebras by K.Habiro and T.Le. But they are all defined only basically for homology, for integral homology spheres. And I'll also report on some my own work on, towards extending these to rational homology spheres. Yeah, for general three manifolds, they're not yet defined. So let me just start by recalling you the story about the quantum invariance. So as you know, more than 30 years ago, Vogt-Jones defined invariance of links. So let me perhaps put it here. So this is my set of links. They will be framed links. And Vogt-Jones defined an invariant which is a polynomial, Laurent polynomial in one variable. So basically the links can be also colored and framed by some representations of, say, I will state first in SL2 setting. And then, so like, the ideas came from physics here. Then, so basically, who fulfilled these ideas was the Kontsevich. So he developed some perturbative extension. So basically, given a link, he constructed an element in algebra of Feynman diagrams, such that there is a well-defined algebraic procedure which is called taking so-called SL2 weight system. I should write bigger here. So SL2 weight system. I just trying to put two diagrams on one board. So therefore it's so small, but so I'll improve myself. So if you evaluate this you get in the ring of power series and one parameter h with rational coefficients, and basically you can finish this diagram by putting here q to be e to the power h, and basically what you get is a commutative diagram. Yeah. So this is kind of the whole picture. So this is very satisfactory because you have something which is defined so in some algebra of Feynman diagram, and you can get back the Jones polynomial here by just evaluating q at e to the power h. Yeah. And you may ask whether something similar exists for three manifold invariants. And in fact, so by doing surgery, so I'll do only for the moment plus or minus one surgery on a link. What you will get is so-called Z homology sphere. So I'll denote this space like this. So these are Z homology spheres. Yeah. So this means that the first homology group with so the first homology group of all manifolds there with integral coefficient is just trivial. So the order is 1. Okay? And again, so you can construct an invariant which is generalizes this Jones polynomial, which is called Richtich-Drive. So this psi here, it's a root of unity. And the target here is just a complex number. You just can associate for any root of unity psi, you associate to a Z homology sphere. So basically, they are defined even for all three manifolds, but in this setting, I'll restrict to Z homology spheres. You get a complex number. Again, so you can make some kind of surgery procedure on this Kontsevich integral. And so this was done by people, by Lie, Murakami, and Tatsuki. You get again an invariant in this space A of Feynman diagrams. Yeah. And then what you can do by applying this SL2 again weight system, you again get a power series in one variable. Okay? But here it was completely unknown how to get from this complex number to this power series. Yeah. So they are called Otsuki series. And this was a long time an open problem. So let me recall you perhaps first how this Richtich-Hinturaev invariant, we are speaking since today is the morning, so perhaps it's not bad to see once how it was defined. So again, in SL2 setting, so I define the following state sum. So my psi, it's an Rth root of unity. So I define these things by taking the colored Jones polynomial, where the colors are natural number, n1 until nm. So I have a link L with m components. I take here this quantum number ni's, product of all of them from 1 to m, and then I sum ni from 0 until r minus 1, where this r is my root of unity. So this is an expression which is invariant under so-called Kirby 2 move. I'll come a bit later who is a Kirby 2 move. But after this, so if you just take this expression and normalize it in a way that for the unknot plus 1,5 framed unknot, and for this expression for the minus 1 framed unknot, taking in the power of sigma plus or sigma minus, this is the number of positive, respectively negative eigenvalues of the linking matrix for L. So after you normalize this like this, you make this expression also invariant under the Kirby 1 move, and so the result is the so-called Richtich-Hinturaev invariant. So this is a VRT invariant of a 3-manifold obtained by surgery on a link L. Yeah, so here M is obtained by surgery on a link L. Okay, link supposed to be framed, need not to be oriented. So this is just a definition of this invariant, and so you see from the definition, it's not clear that that this thing should be an integer, so algebraic integer. This probably is the first thing you need to check before you start to say, think about any categorification of this guy. Yeah, so it would be nice to have coefficient here to be integer, because you would like to have to interpret them as the dimension of some spaces. And this was basically our theorem. So it was together with Chen and Tang-Li, 2008, I think we proved that this guy is in fact an algebraic integer for any psi and any 3-manifold m. So independent of the root of unity and the manifold, it's always an algebraic integer. And this theorem basically, it has a long history. So like by hand using some skein theory, Masbaum, Roberts proved this for the case when R is prime. So in the case of prime root of unity, this was known a bit, so this was perhaps 2008, and this was really based on the Habiro methods, so our proof. I'll perhaps come back to this, but so this was in the late 90s, so it was much in advance. It was known that the theorem holds for prime roots of unity, but there were no tools to extend the proof to all roots of unity, because it was really specific properties of a prime root of unity. And then the first proof when M was homology sphere, so when M was the homology sphere, so this is due to Habiro, and this follows from his unified invariant theory, which I will basically talk about today. And so we generalize this result by using his method to all manifold at all roots of unity. Okay, so Habiro, it was R arbitrary, so any R, but a restricted set of manifolds. Okay, so let me start now to speak about this Habiro ring. So this is a ring which is constructed from polynomial ring with integral coefficient in one variable by looking at the ideals there. So you, for example, you can define an ideal generated by such a guy which is looking like quantum factorial, 1 minus q, product of 1 minus q, 1 minus q square until 1 minus q to the power n. So you look at the ideal generated by these products, and you call this ideal In. So clearly you can find In plus 1 inside of this In, and you can also continue in this fashion, and you will have infinite projective system of ideals inside of this polynomial ring. And now you defined your so-called, so this is a notation. ZQ hat is a notation for the Habiro ring. You define as the limit when n goes to infinity of the quotient of the q by this system of ideals. Okay? So how should you think about such an element f into this ring? So any element can be represented as a polynomial in Q. This is just an honest polynomial. So this is just in Q. So you don't need Q minus 1 here. It's just polynomial in Q times the guy. So this is abbreviation for this guy is a QN. Okay? And so I sum from k from 0 to infinity. So it's an infinite sum. Yeah? So in some sense, you define topology on this space by saying more your polynomial divisible by cyclotomic polynomial, far away is this thing in this topology which you define, this so-called cyclotomic completion of a polynomial ring. Okay, and now so one nice thing which you immediately realize is that it's very natural operation in this ring to evaluate this f at some root of unity, because what happens is that all these guys who are longer than the order of your roots of unity, they become 0. So basically, it stays a finite sum after you evaluate at the root of unity. So what happens is that here you go only from k from 0 until r minus 1, and you take this expression and you just evaluate at q equal to x, and the things become finite. So this evaluation are well defined. And the other interesting thing about this ring is that it's admit so-called Taylor expansion. So these are all theorems of Habiro. So about properties of this polynomial ring. So first says that there is an injective map from this ring to such a power series in q minus psi for any root of unity psi. Such a map is injective, and this map is defined by sending f to basically to the Taylor expansion of f at the root of unity psi, which is defined as a sum nth derivative of f in the place psi, so like this. And the fact that this is injective means that f is equal to g in this ring, in the Habiro ring, if the Taylor expansion of this function coincide at one point. So basically, these are functions which are determined by their Taylor expansion in arbitrary points. So this is a well-known property of analytic functions. So therefore, this ring is always, so it's often called ring of analytic functions at roots of unity. So this is exactly the property. And another interesting property of this ring is that, for example, if you put you have an injective map from here in the power series in Q minus 1. Yeah. So if you take just, instead of this root of unity, you put just 1, then you have an injective map from here into the power series with integral coefficients in 1 minus Q. Okay, so these are a few properties. And the last properties I wanted to mention about this ring before I state the main theorem is that it's also, so this is second theorem, it's also due to Habiro. So you have another injective map from the Habiro ring into the evaluations. So this is map given by the evaluation at the root of unity. But interesting is that I can still have injective map if I take any set Z here of root of unity which contains infinitely many prime power order elements. Yeah. So these are two properties which I'll refer later. And so basically the main theorem which I'll speak about today. So I'll really now formulate the theorem and then try to argue how the proof works. So this theorem, this is due to Habiro for G is equal SL2. And this was about 2006. Yeah? And the second one, it was Habiro-Le, so more than 10 years later. And double as much pages. So this was for G, so this is, yeah, okay. So I mean, paper was 80 pages based on another 100 pages, and this was 120 pages, so okay. So the main theorem says that assume you have three-manifold, which is a Z homology sphere. Then there exists a unique element I of M which belongs to the Habiro ring EQ hat such that evaluation at any root of unity of this guy is equal to the Wittner-Stich-Into-Rayev invariant at this root of unity. Yeah, so this is why this, so this is kind of power series invariant, yeah, which evaluates at any root of unity to Stich-Into-Rayev. So it's, you can see, think of it as a generating function for the whole set of these invariants. And therefore, it's called unified invariant. So Habiro's name for this was unified invariant. So this is why my talk is called like this. And you see, what you immediately have as a corollary of this statement is, first of all, so the first corollary is that that this thing, so Stich-Into-Rayev invariants are algebraic integer for all root of unity psi and for any m in the set of Z homology spheres. So this is the first application. Then that the set of all Stich-Into-Rayev invariants is determined by evaluation. So for any, so evaluation, for example, on just on all, so you can give me a prime, your favorite prime, for example, 2, yeah? And so if I evaluate these things just on all prime powers of 2, then it's enough. Then I have the whole information which this set contains. Yeah? You can also take 3, or you can take whatever you wish, just any set which has infinitely many primes. Yeah? So this is kind of strong statement. It was before no method available to study this set of invariants as a set. Yeah? So it was only available like pointwise. And the last consequence of this theorem is that so-called Otsuki series So this is this expansion which is still here on the board. So this is called Otsuki series. If you take LMO invariant and you plug in some SL2 weight system here, you get this. This is Otsuki series. Then this Otsuki series have integral coefficients. So now I can illustrate probably here on this diagram more precisely. So what this invariance in so it really completes this diagram in a quite a satisfactory way. So it says that there is for any element M here inside there exists guy who is unified invariant sitting inside of Habiro ring. Then from this Habiro ring you can obtain Richtlichen drive by evaluating at the root of unity, and you have Taylor expansion in Z1 minus Q, which sits inside this ring, and basically so this provides here commutative diagram, and here also. Okay, so this is how everything fits together. And now let me perhaps just as commercials sell a few results which how we extend this to the homology spheres. So around 2008, so together with my student and T.Le, so we had a statement that given M in the set of rational homology spheres such that the order of the first homology group is equal to the B. So this is just some integer, some positive integer. There exists also unique invariant I of M, which belongs to something similar to the Habiro ring. The only difference is I have to invert. Yeah, perhaps I write it like this. So I have to invert the order of the homology group. Yeah. So it's not any more integral domain as it was before. So before the Habiro ring itself is an integral domain, as you see. So it has an injective map into this power series, which are integral, and this ring splits into a product of rings, basically for each prime factor in this B. So if B is just a prime, then you can so you have it's not that all prime number are equivalent in some sense. How it was here? Here it was this Z. It was just any set containing infinitely many prime numbers, and here it will depend whether your prime number is coprime to primes here or not coprime, and it will have different behavior to roots which are coprime to order of this B and which are not. Yeah. So okay, such that evaluation at any root of unity of this guy IM is the Richtlichen drive of the rational homology sphere. And finally, together with Christian Blanchet and T.Le again, we also constructed some, so in this case, B was 2 to the power n. So if you have a rational homology sphere with order of the first homology as a power of 2, then we constructed some invariants which unified the spin and the homological refinements of this Richtlichen drive invariance I. So in this belongs to a little bit different. It's also kind of cyclotomic completion, but not exactly like that. Okay, so this is what I wanted just to mention, and now so let me concentrate on the proof. So this was basically, so this is will be now until the end what I will try to explain, proof of the main theorem. So basically, so I myself, I realized just recently that this proof goes back to a work of Hennings, which was made in Cambridge in 90s. So it was the idea really, I think, due to him and perhaps few people before him. I'll also mention, so it was 1990s, so here. And the idea was, so why should we study the representation of some algebra instead of studying the algebra itself? So why, so the idea was why we cannot define such an invariant without referring even to any, here to any colorings, yeah? So here basically, so if you look, such a sum plays the role of a Kirby color, where so you need kind of semi-simple category with finitely many different colors, such that anytime the product decomposes into these simples here, and then you can write down such invariant in this form. So Kirby color is sum over these quantum dimensions of some representation, and so on. And so he say, I don't want to go into this representation theory, so it can be complicated. So why not to consider something which is Riemann-Hopf algebra itself? So this is so-called Riemann-Hopf algebra. Okay, so this means, so you can think about this UQSL2. This is the R matrix, and this is the Riemann element, which is just describes the twist on the Riemann. So this is a triple describes so-called Riemann-Hopf algebra. So Turai, for example, developed a general theory how starting from such a thing obtain so-called modular categories, so in some sense, and then you always have this Wittgenstein-Turai invariant. But Hennings was looking just on that, and then the next ingredient was so-called universal invariant. Then out of this triple, one can construct universal invariant of framed links. And for those who perhaps haven't seen this construction, I'll just briefly recall. So basically, you can obtain, so even not from even framed tangles. Yeah, so any tangles you can build by composing the following simple pieces. So, for example, that one, or the opposite one, or there perhaps with inverse orientation, and perhaps some caps and cups. So I'll need only a few of them. So I'll need that one and that one. Okay. So to this guy, you associate the R matrix. So R matrix you can write down symbolically as alpha tensor beta, and what you're putting here alpha, and here you're putting beta. So the inverse of the R matrix I'll symbolically write as alpha bar tensor beta bar, and here I'll put here alpha bar and here beta bar. And so here I put so-called balancing element G, and here it's inverse. And this balancing element, so basically it's can be built out of Riemann element, which I called here, I think, V minus 1, U, and U it's something like S beta times alpha. Okay, so there are kind of few numbers which you just put on your link diagram, yeah, and then you go along, so opposite to the orientation, and you read the word which is written on your strand of your tangle. And in general, what you get, it's invariant of tangle. So if the tangle consists of n strand, then the invariant will be here in some power. So it's more precisely, it's in some invariant part of this, but we will not touch it today. And so let me just give you an example. So the most important tangle we will consider today, it's so-called clasp tangle. It's even bottom tangle in sense from Habiro, because it's like all endpoints are on the bottom. So therefore it's a bottom tangle. Yeah, and so now if you apply this thing, so these rules, then what you realize, so you cannot really exactly apply this one, because so one orientation here is reversed, and if you reverse the orientation, you have to apply S. So this is an antipode in the Hopf algebra to the corresponding element. So let me do it. So just for this tangle, so this orientation is okay, so it's alpha, but this orientation is reversed, so it's S of beta. Okay, and then I put them in the different colors because there is summation index between these two, and there is summation index between the other one. So I just I don't want any indices. I just put colors. Okay, and then the other guys. This is here. This guy is reversed. So this is S of alpha, and this is beta. And now, so if I call this tangle C, then G of C, which I'll sometimes also call C, it's just a sum of, so now I'll put here S of alpha. So I have to go so opposite to the orientation and read the word on the strands. So here it will be S alpha, S beta, tensor, and here a reversed orientation alpha. Oh, sorry, it should be a red alpha, and so this is exactly the invariant. Yeah, and you can recognize perhaps that you can obtain it by applying. So S, it's anti-homomorphism. This S times identity to so-called monodromy matrix, which is product of two matrices, the R matrix and 2, 1, which is just reversed, so with a flip. So this is called M, and this is the monodromy matrix, which kind of will play a role. Okay? Any question about?
Why are there no G's?
Why?
Yeah, should there, I mean, in your correspondence, should there not be a G corresponding to the maximum?
I forgot to say this. This is exactly the orientation. It's chosen in the way. So all caps and cap which are not here, there is nothing assigned to them. So here there is a cap which is like both caps are like this.
Oh,
so
pointing to the left.
Exactly. So so I'm exactly missing this. So this. Yeah, so it's a trick, yeah. So, but it's like that, yeah. So I only put those who are non-trivial, and everything else is not. Okay. Other questions? Okay. So then I probably go here. So the statement is that what you get is invariant of a tangle. So after doing this. And moreover, so the statement, so for any tangle, is the tangle invariant, and moreover it dominates all the colored Jones polynomial, whatever coming from this algebra, in the following ways, that you can just take trace in any representation, so-called quantum trace, tensor all these quantum traces for different representation, apply this to GT, and you get a colored link invariant obtained by closure. Okay. So this is why. Habiro is working with bottom tangles. So he is not closing them. So he don't have G here in this GT, but he is becoming this. If you know how this quantum trace is defined, it's defined by putting first G and then the whole expression. So basically this is, so the G's are here already. So therefore what you get, it's basically it's invariant of a closed link colored by this representation. So it's, in some sense, it's, so it has the same information as the whole system of colored invariants. So it's better, in some sense, to look at this invariant in the Hopf algebra itself, instead of studying the representation theory. So this was the idea. Okay, but then, so this is very nice, but how to come, so how to do this step here, yeah? So we basically, so with this GL, we have something which dominates all this kind of invariant, but we're still not with the three manifolds. So in order to obtain three manifold invariant, you need something what is called Kirby color, yeah? And Kirby colors is, in this picture of Hennings, is played by integral. So an integral, it's a special element of the Hopf algebra, of the dual of Hopf algebra. So Kirby color in this setting is played by some element mu of, so more precisely, so this is so-called quantum character. So this space of quantum characters, it's just all functions on H with a property that, so it would be just a character if it would have trace property, if I would just exchange this x and y and it would stay invariant. But it's not, so it's a quantum character, so it goes like this. And basically this S squared is just conjugation with a G, with my balancing element G. So CF4 is related to the quantum. So for example, CF4, all quantum character are inside. So all these guys are elements of this set. But this is a very special one, this mu. So this mu is defined by property that mu tensor identity applied to the co-multiplication of x is equal to the mu of x times identity. Okay, and this has a great interpretation, geometrical interpretation, because so if you have a component, closed component, which can be noted and linked with any other components. And after I read off, I'm using this algorithm for constructing the universal invariant. So I read off some word on this component, which will be just an element x. Yeah, for example, in my example, this x, it will be such an expression of these alphas and betas, s's and g's, and whatever will come. So I have this x, and I have some other component somewhere, which also can be linked and noted and whatever. Yeah. But I know the very nice property of this universal invariant that if I slide this component along this other component, so if I would like to slide it like this, then what happens is that on that place, instead of x, I'll have delta of x for both of these components. So this will be delta of x. This is exactly how the universal invariant behaves under sliding of one component along the other. And now if I evaluate mu on that component of this delta of x, this is exactly the same as I had before. Yeah, and this is basically the set that so this is the theorem of Hennings, that if I take just mu to the power m, or n I call this, and evaluate with this dual element, if I evaluate, so each component of my tangle, then what is the result is invariant under Kirby 2 move. So this is what I wrote here. It's exactly the Kirby 2 move. So this gives you already an invariant. So because you know exactly as in the case of Richtich-Hinturaev invariant, so Kirby 1 move is just equation of normalization. But in order to be able to normalize, you need one important property. So you need that. So this is basically which correspond now to the invariant of the plus or minus 1 framed unknown, which should produce a 3. So see, for this guy, it should be, so I should normalize by this to the power sigma plus and sigma minus. So this guy should be non-zero. Yeah? And this is exactly, this condition is exactly equivalent to something which is called that my H is factorizable. Okay? And this factorizable, it was discovered by different people in different contexts, so I'll give you now probably 3 different definitions of what does it mean that Hopf algebra is factorizable. And so this is probably the first even, yeah? So this is equivalent. So for example, H is factorizable if, so this is just different definitions. If the Hopf pairing, which always can be constructed on a braided, on a Riemann Hopf algebra, it always exists, such a Hopf pairing. So K are my scalar, and this Hopf pairing is characterized by the property that omega of A times B paired with D is the same as omega A paired with D1, omega B paired with D2, where these are the parts, this is Swede notation for the delta of D. So this means that with respect to this Hopf pairing, multiplication and co-multiplication are joined to each other. So this is the definition of the Hopf pairing, and it's given by exactly what you think by the Hopf link. Yeah. So probably he also realizes this factor. But so this pairing is non-degenerate. So this is one definition. So the second definition of this factorizable is that the Drinfeld map, which I'll call D, big D, going from H star to H, which is basically goes like this. You take F here and you send it to F times identity evaluated at the monodromy matrix. So this map is isomorphism. So this is a very nice map if you restrict here to quantum character and here to the center. Then perhaps you have seen this. This map will, in many cases, will be. So if you take quantum character for the representation V, then according to this Drinfeld map, you'll send this quantum character to the central element, which you get from the Hopf link. If you take the universal invariant of this Hopf link, you plug in here the quantum character, and you left this component open. So this will give you a central element in the Hopf algebra, and this is it's an algebra map from the Grothendieck ring of your category to the center of the ring on the center of the Hopf algebra. So this is just restriction of the Drinfeld map to the quantum character. But you require that this guy is an isomorphism. Yeah, this is another characterization. So I'll give you a third characterization. So the third characterization is that this clasp element, which I wrote here, so this clasp element can be written in terms of Ci tensor Ci price is Ci2 prime. So in this way, so here it's some basis of your A exactly, and you require this and that one are dual basis with respect to omega of your Hopf algebra H. Yeah. So you can think about PBV bases. They are not the same, but they should be dual to each other, and they should be bases. Yeah. So this is what it means factorizable. That basically, if you write this clasp element, then you sum over all elements in the algebra. Yeah. And not so sometimes it's not. So it's very often it's not factorizable. Okay. And after you know what is factorizable, then the main theorem of Henning's says you that I'll adapt now his main theorem, perhaps on that board. I'll adapt this to the Habiro setting. So I'll only formulate this for the homology spheres. However, so it doesn't need it. It will have a nice formula. So see if I'll do this way. So adapted to our setting, so corollary of the Henning's theorem tells you that if you have a factorizable Riemann-Hopf algebra, then this would be also the homology sphere. Then you can obtain an invariant. So I call this G of M by applying mu r plus minus 1 m times of to G of T0, where just T0 is a zero-framed algebraically split tangle whose closure is exactly my Sadger link L0, so it's still zero-framed, yeah. And mu r of x is defined as mu of Rx. So it just you shift this form by this ribbon element. Oh, sorry, my ribbon element was V, yeah. So I'm sorry. So it's still the same. It's this V. I'm sorry. Sometimes I'm R and sometimes I'm V. So. Okay. And so this is basically what the theorem says. Yeah. So if you take universal invariant, so this is an element in h to the power something, yeah, and you evaluate each component with a form on your Hopf algebra, yeah, then you get something which is invariant of. So this is topological invariant of M. Of your the homology spheres. So in Habiro paper, they call this twisted form, or twist form they call this. So they never speaking about mu, so the connection is not completely evident from their approach, but this is exactly what they're doing. So it's just, and then the only question, so basically you see, so this is 1990, so this is a corollary of a theorem which was like really long time ago, yeah, and the paper of Habiro and T.Le 2 years ago. So what the people did in between, yeah? And so basically what they did is examples for this Henning's contraction and construction before were basically made for finite dimensional Hopf algebras. And to obtain finite dimensional Hopf algebras, you take a quantum group, you evaluate at some root of unity, and then you have something finite dimensional. You have only finitely many elements in PBV basis. What Habiro and T.Le did, they don't evaluate. So they were working, they take for H really UQ SLN, for example. So really huge, so infinite dimensional algebra. And they constructed inside of this algebra some kind of integral part. And this is not the Lustig integral part, so they define themselves something which is adapted to this dichotomic completion. And then for this algebra, they could prove some analog of factorizability in the integral sense, and then apply the theorem and say that the result is indeed in this ZQ hat. Yeah. But basically, so there are, I have another few minutes.
Where does JM live?
Sorry? What?
So where is
so here it's just your K. Yeah. So you evaluate, so like, yeah, so you evaluate this. Yeah. But exactly, but they were more precise who is K. Yeah. So they could do it better, and to do it better, so they basically there are two main ingredients to how they improve this ring here. Yeah. So the first is algebraic and geometric ingredients. So let me do it here. Or is it that visible? Is that visible? Okay, so let me do it here. So basically, so they defined the following ZQ hat submodule of h to the power m, so which consists of all elements which looking like this. So k is from 0 to infinity, and xk is an element in h to the power k, sorry, h to the power m. So this is where it's m, so this is a submodule, so this will be ZQ hat submodule of h to the power m. But here this xk, it belongs to, so first of all, integral part, and secondly, even part. So if you think about how it really look like, so perhaps you remember how this monodromy matrix looks like. So it's like huge sum, and here you have some f I k p e I tensor f. So basically it's the same even. So even f j k something also. So you have such an expression. You sum over all these indices, and the problem is also that you don't have. So usually here you have just one. So you have a denominator which corresponds like to something like this. Yeah. So you don't have. So you cannot write it in loosely canonical basis because you have not enough denominator here. So and what they consider, they consider a square of this guys. So they make sense to this. This they call integral part, and then you call even part. It's if the power of k is always even. So the power of k should be always even. Yeah, and this they called like ZQ hat submodule of this h to the power m. Okay, and then so their main technical theorem was of Habiro and T.Le. It was that GT0 belongs to this guy. And out of this, it immediately follows that mu r plus minus 1 evaluated of GT0 is element in Habiro ring. Okay. And so the proof of this fact is quite often involved, and this is another paper of 100 pages. And in this other paper, what they construct basis or presentation of the category of bottom tangles. So basically, they say that any bottom tangle, so this is the main geometric ingredient, any bottom tangles you can obtain by composing Borromean tangle. So this is a Borromean tangle taken few times together with element of this guy of double, and this double it's basically is a composition and concatenation of the following tangles of Z1, 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 and Z1. And everywhere here the orientation are in that way that there is no so it's everything is algebraically split. So everything here it's algebraically split. Okay, so these are basically the genius. So you obtain any algebraically split tangle. This is a very strong fact by starting with the Borromean one and applying these things. And here they use some, again, deep theory of Kerala, Lubashchenko, and so on. So they interpret these guys as a Hopf algebra. So they interpret basically this H sitting inside of the H. So consider it as a regular or adjoint representation of itself. So H is a adjoint representation of itself. It's a Hopf algebra object inside of H mod. And these things, exactly, it's a Hopf algebra operation. Like this is a braiding of this Hopf algebra, this is co-multiplication of this Hopf algebra, and this also can be composition of some Hopf algebra operation in this H mod. And then out of all this stuff, you get a bot that if B, so it's just by computation for the Borromean ring, you just show that this belongs to K3. This is just a computation. So this is Borromean ring. So Borromean tangle has 3 components. So this is an element in K3 by computation. And then they prove that all these operations are K admissible. So if you are already in such a submodel, they do not destroy this integrability, so integrality properties. So this means basically from this only computation, yeah, in some formal properties, some Hopf algebra arguments, they get this quite an amazing fact. Yeah, and after this, so this is just fall down just by, that's very easy. That the guy is immediately in the Q hat. So if I'll need perhaps 5 minutes to illustrate how it so in very concrete how it works for SL2, if you wish. If not, I can stop here. Wine reception is more important.
You have a minute, yeah.
Yeah. So should I? So okay. So this is the only case where you immediately. So this is what physicists always saying, that you can get this power series, so these elements here by some kind of modular transformation applied to blah blah blah. Yeah. So as far as I know, it's only work for SL2, because in SL2 you have an explicit basis, so you can. Let me argue for SL2. So for SL2, you just very explicitly can construct this Kirby color and the basis C prime and C2 prime I was talking about. So these 2 bases are known explicitly, and therefore everything is like easy, and you can go from center to the Grothendieck ring by this Greenfield isomorphism. So you can jump from center to characters here, there, and so on. So therefore it's so it becomes very explicit. So let us just take a note. Yeah. So G of K0 in the case of SL2 can be written as some integral coefficients times sigma n. So this is the universal invariant, and this sigma n, it's the following expressions. It's product I from 0 to n, and here you have square of the Casimir. So C is square of the Casimir minus some eigenvalues of the Casimir. So it's such a product. So it's so you remember already it looks like, so if you evaluate, it looks already like Pohammer things. So this is exactly the fact that this is even part. So remember that Casimir itself has some K's inside. So Casimir itself looks like EF minus FE plus QK plus Q minus 1, K minus 1, something like this. But here it's square, therefore it's everything, it's only even power of K happening. So therefore it's in squares and not just in the thing. Then mu r plus minus 1, it's a form which looks like some integral coefficient, and here traces in some guys which are called Pn, and Pn are defined as 1 over n factorial, quantum n factorial, of a product I from 0 to n minus 1. Here it's a fundamental representation, minus 2i plus I minus 2i minus 1. So this is an element of the Grothendieck ring. Yeah, so it's a color, so it's a quantum trace. Yeah, so it's a trace in this color, in this representation. Okay, so now if you would like to evaluate this mu r plus minus 1, again I switch to r, v plus minus 1 on g k0, then this is basically amounts, so you have a double sum with all the coefficients, and then you take trace q of Pm in this sigma n. And this is basically known to be just a Hopf link where you color, so it's a Hopf link where you color this guy with Pn, and the other string you color with Sm, where you get Sm out of this sigma just by replacing, so just this Drinfeld map sends the two-dimensional representation, the defining two-dimensional representation of SL2 is sent to the Casimir. Yeah. So this is the correspondence between the two. So you get this Sm out of the sigma n if you insert here V square. Yeah. So these are two colors, and they are known to be orthogonal. So the invariant of Hopf link with these two colors known to be like this, and here it will be 2m plus 1 factorial, something like this. Yeah. And you see it's a huge divisibility here by 2m plus 1, and it's this factor which you have here, and still so basically they should be equal. Yeah. So you have 2n plus 1 here divided by n factorial. You still have a lot of divisibility, so a lot of factorial, so that the result here it's still divisible by at least qn, and so therefore the whole thing belongs to the Habiro link, like this. Yeah. And now, so after you know this explicit basis, so, and this is basically your Kirby color. You know that the Kirby color should be written in these PNs. Yeah. What you can do, so if you have just your normal expression for the Richtich-Reif invariant, so you know the problem there is that you have GL with all this representation here. Here's in quantum dimension, and then you sum over all of them. Yeah. But now what you're doing, you're just doing basis change. So you put here these PIs, and here you have your basis change, which goes from your NIs to PIs. So basically the whole dependence on the link is in this constant, which do not depend anymore on the summation indices, because the summation indices only affect kind of a standard part. This is called modular transformation. So this is the only place where NIs now coming, and the whole rest, so this Kirby summation only affects the standard part. And you just can compute this, and this is kind of apply some Roger-Ramanujan identities, and you will get basically invariant of a 3 manifold, basically as just invariant of a link with the correct colors. And this coefficient AI, so this one. So this is how you can, at the end, when you know that everything works, you can try to work out this modular transformation just by coloring link already with the correct colors and simplifying the rest of the definition of Richtich-Reif. Okay, thank you very much.
Any questions?
This may be an unfair question, but I mean, so how is this construction you were just telling us about supposed to compare with the construction that Kummer and Pavel? I mean, again, you get,
yeah.
They're producing some power series in Z of Q.
Yeah, this is, I don't understand. So, why, so I mean, it doesn't make sense here to speak. So I don't understand how you evaluate.
Oh, this is series convergent in the side unit circle, and then you take an outwards limit, root of unity, and the limit exists, and you see WRT.
So these things are defined only at the root of unity. Yeah. So the whole story here is defined. So I don't know how it behaves inside of the ball. I only know how it behaves in the roots of unity, and this is kind of nice behavior really on the circle. Yeah. So
you say there is no way to produce some analytic function from the Habiro.
So probably it's your analytic function. I just don't understand.
I mean, we have some sort of series in Q, power series in Q, but the statement that they are convergent in the units inside the unit circle, and then you take a limit. to the root of unity.
So it should probably how do you how you would produce? So I mean it will be an infinite sum here if you
Yes.
in Q. So in which sense it should converge?
It's,
Inside. So inside it's not
Inside.
defined. Yeah. So
I guess activity that
Some
you
of them are
express is
associated
very
with
different
the
than
word
what you
surface.
showed in the first one.
exactly, it's very different. Exactly, it's very different. Yeah,
Environment.
yeah, exactly. It's probably very different. Yeah. So it would be nice, clearly, to have comparison. So I can. So I have in few cases like twist knots, Poincaré sphere, plus minus one surgery on the trefoil, and so such things. So I have very explicit formulas. Very explicit.
I mean, I know for some examples you can, I think, look very formally to re-expand this element. I mean, if you write the formal expression with the element of Habiro ring, you can formally re-expand it in Q, and you get some sort of convergence. But this is not always. This is a very formal procedure. It's not I think you can do this, for example, for if you start with surgery on the trefoil. So and
Yeah. So for the trefoil, you will get something which looks like basically just power. So some power of q, something like this, and here you will have q to the power 2i plus 1, probably q I, something like this, and here plus minus. So this will be such an expression.
I think in this case you just like every term you like write as a polynomial q, and then like each higher order has higher order of q, so you can there is sensible it's sensible to transform in q, and when you do it this way you obtain this series in q, which we obtained by lowering the gear in this particular case.
So I would claim that its coefficient of the theorems are by no way any invariants. So just no way you will get, because it will be a mix of Rishi into Rai for different orders. So
I mean, I mean the coefficients of this q series are there are no direct relation to
exactly.
convergence. What I'm saying, you have to sum up the series, make it into analytic function, then take the limit to the root of unity.
And this analytic function should be defined inside of this ball.
Inside.
So I guess the very interesting question is there a way or a map or an operator from the Habiro ring to functions which are analytic in Q inside the unit circle and has limits as Q goes to a root of unity that's exactly given by the...
Yeah, and I think it's completely open. Isn't it?
Yeah, I know.
Yeah.
Any other questions? Let's think at it again.
Time for a break.